everybody, and welcome to Lesson 2.2, Geology. The content in this video is aligned to the third edition of Environmental Science for AP and covers information from College Board Unit 4.1. Now that we know how nutrients are moved through the various parts of the Earth, it is important for us to understand how the basis of this system is formed and how its processes change the way the rest of the system functions. This leads us to the content objective of understanding that Earth's systems interact, resulting in a state of balance over time. By the end of this lesson, you should be able to identify the parts of the Earth and their function, describe the geological changes and events that occur at convergent, divergent, and transform plate boundaries, describe geologic time, explain how natural processes and structures can be used to describe Earth's history, compare and contrast the different types of volcanoes, explain what happens at the moment an earthquake occurs, and explain how earthquakes cause tsunamis. This leads us to being able to answer the guiding question: how is the Earth a dynamic system? To begin, it is important to understand that the Earth is billions of years old, 4.5 to be exact. We can break up what we call geologic time into different stages, each with very particular characteristics. Time is broken down into eons, eras, periods, and epochs. Notice that the vast majority of Earth's history is in the Precambrian eon, prior to the development of complex life that would come to permeate the planet during the Cambrian period. We are part of the Holocene epoch. It is possible for us to understand the age of the Earth and the things we find in rock layers by using a variety of dating techniques. We can break these up into radiometric, or absolute dating, and relative dating. Radiometric dating is done using radioactive isotopes that are found in living things and rocks in known quantities. We can calculate the age of rocks, for example, using the half-life of an element. The half-life is the amount of time it takes for one half of the existing element to decay into another element. For the age of rocks, we often rely on potassium-argon dating, which can be accurate from 4.5 billion years all the way down to more recent hundreds of millions of years. We can also use what is called relative dating, which tells us the age of a layer of rock or something we find in it based on its relationship to something else. For example, we use stratigraphy to explain how layers of rock that are lower in a profile are older than the ones nearer the top. Given that processes like volcanoes and earthquakes can cause drastic changes to these structures and how they appear, stratigraphy is a useful way of identifying a general timeline. We can also use what are known as reference fossils, which are fossil remains that we have a definite age for. In this way, we can say that rock layers in which these reference fossils occur must be of a particular age. Now, in order to understand the ways in which the Earth's components fit together to interact into its various systems, it's important first to understand the structure of the Earth itself. In general, the Earth is divided into three major sections: the crust, mantle, and core. The crust refers to the parts of the Earth upon which we walk. This solid rock, broken up into what we call tectonic plates, and the solid structure beneath it is known as the lithosphere. Beneath that is the mantle, which makes up the vast majority of the mass of the Earth. The mantle is made almost exclusively of molten rock of varying compositions of silica and oxygen. The upper component of the mantle has a plastic-like consistency, and is the component upon which the tectonic plates move. This section is known as the asthenosphere. Lastly is the core, which is divided into inner and outer sections. The outer core is liquid and made largely of nickel. The inner core is solid due to the extreme pressure of the rest of the planet and is made up largely of iron. It is this inner core that has allowed the Earth to develop protective magnetic fields. The lithosphere is divided up into smaller sections, known as tectonic plates. Each plate is made up of one or more types of rock, continental or oceanic. Oceanic rock is thinner but much more dense and is made up of a type called basalt. Continental rock, however, is thicker, but andesite, which it is made of, is much less dense than basalt. Some plates are very large, such as the Antarctic plate, and some are very small, such as the Juan de Fuca plate. These plates float on the asthenosphere, which is continually moving due to the process of convection. As the liquid rock of the mantle, known as magma, warms, it rises. This rising causes the lithosphere above it to melt just slightly and makes it easier for the plate to move along this liquid structure. Cooling magma falls back toward the core, which continues the process of convection. In this way, the plates that make up the surface of the Earth are continuously moving. Because the plates of the lithosphere are moving, they come into contact with each other in a variety of ways. There are three general categories of what we call plate boundaries: convergent, divergent, and transform boundaries. Let's look at each of these in turn. Convergent boundaries occur in three types based on the kind of plates that are interacting with one another. At a convergent boundary, two separate plates come together. When two ocean plates meet, known as an ocean-ocean convergent boundary, the plates meet and fold under together, forming a trench. When an ocean and continental plate meet, known as an ocean-continent convergent boundary, the more dense oceanic plate will slip beneath the continental plate in a process known as subduction. These plate boundaries are known to cause volcanic mountain ranges that occur on the edge of continental plates. The last type of convergent boundary, the continent-continent convergent boundary, occurs when two continental plates meet. In this case, both plates will fold upward, leading to the formation of mountain ranges such as the Himalayas. Because the Earth's circumference is not getting any larger, if a convergent boundary occurs on one side of a plate, a divergent boundary must occur on the other. Divergent boundaries occur when two plates move away from one another. These types of boundaries lead to seafloor spreading and the formation of underwater mountain ranges, such as the Mid-Atlantic Ridge, and continental rift zones, such as the Great African Rift Valley in northeastern Africa. Lastly, there are transform boundaries, which we will explore in more detail later. At these boundaries, plates move past each other, either vertically or horizontally, storing and releasing large amount of energy in the form of earthquakes. The rock cycle is the way in which the various pieces of the lithosphere interact to recycle the elements that make up the rock on our planet. There are three categories of rock based on their formation and composition: igneous, sedimentary, and metamorphic. Each of these types of rock can be converted into others through a series of processes such as melting, crystallization, weathering and erosion, heat and pressure, and others. Let's look at the process in a general overview. We'll begin with magma, which is molten rock that is beneath the surface. When magma cools and crystallizes, it forms igneous rock. This rock can be intrusive, found beneath the surface in another rock layer, or extrusive, found on the surface. When igneous rock undergoes weathering and erosion, it forms sediment, which can be deposited and compacted to form sedimentary rock. Igneous rock can also be put under heat and pressure, which turns it into metamorphic rock. Sedimentary rock can melt during processes like subduction and form magma, which will then be used to produce igneous rock. It can also undergo heat and pressure to form metamorphic rock. Lastly, metamorphic rock can be weathered and eroded, where it will form sediment and eventually sedimentary rock, and it can also melt during subduction to form magma to form new igneous rock. Igneous rock is produced during the process of volcanism. While we tend to think of volcanoes as violent explosions with pillars of ash and dust and flowing lava, not all volcanoes occur this way. In some cases, there are simply vents or cracks in the lithosphere that allow magma to rise to the surface and ooze out as lava. However, there are four major types of traditional volcanoes that you should be familiar with. The first is the shield volcano, which is often associated with a lack of ash and smoke and gently flowing lava. The shield volcano is named after its low profile and wide diameter, which resembles a shield. The Hawaiian Islands are an example of shield volcanoes. Next is the dome volcano, which produces a moderate amount of ash and smoke, but very fast and thick-flowing lava. However, the steep convex slope of the volcano and the thickness of the lava makes it cool quickly, which minimizes damage. There's the ash and cinder volcano, which produces very little lava, but vast amounts of ash, soot, smoke, and cinder. When lava does come out, it is often in the form of partially crystallized lava bombs. Lastly, there's the composite volcano. This is the one that you're most likely familiar with. Composite volcanoes have violent eruptions that spew lava, ash, soot, and cinder into the atmosphere, along with very damaging lava flows. Classic examples of composite or stratovolcanoes are Mount St. Helens and Mount Vesuvius. Volcanoes don't just occur in static locations like the borders of continental plates. They can form in the middle of plates as well. In order for this to form, there must first be what is known as a hotspot. A hotspot is an area of superheated magma that will rise due to convection and seek a crack or fissure in which to reach the surface. These occur most often on oceanic plates and form what are known as volcanic island arcs. Here we see the formation of the Hawaiian Islands. Oahu and Kauai are the oldest of the islands, but are the smallest. As the Pacific plate moved westward over the hotspot, other islands formed as the plate pulled the hotspot plume with it, allowing larger islands to form even as the plate continued to move. The largest island, the mainland island of Hawaii, only began forming about 700,000 years ago. That is also why it's the only Hawaiian island with active volcanoes. The Aleutian Islands off the coast of Alaska and the Japanese archipelago are also examples of volcanic island arcs. Now that we understand volcanoes, let's look at the other major process associated with the movement of tectonic plates. Remember that transform boundaries are those at which plates move past each other, either vertically or horizontally. The location where two plates meet in a transform boundary is known as a fault, such as the San Andreas Fault in California. The plates move slowly, often only an inch or so per year, but this motion builds friction. Eventually, the plates will get stuck together, while friction continues to build until it is released in one rapid slip strike of the plates moving. It is this rapid movement that we know as an earthquake. The exact location on the plate where the movement occurred is known as the focus, or the hypocenter. Directly above the focus on the surface is what we know as an epicenter. It is from the focus where the seismic waves originate, and we can use these waves to predict specifically where the earthquake took place. There are two basic types of seismic waves, body waves and surface waves. Body waves are broken into two further categories, P waves and S waves. P waves are those that arrive first to a seismograph. These can travel through both solid and liquid, which allows them to move through both the mantle and the entire core. P waves cause the back and forth motion of the ground. S waves are those that arrive second to the seismograph and can only travel through liquid. These waves cause the up and down motion. Surface waves are those that cause the damage that we see on the surface. Rayleigh waves are those that cause a rolling motion, very similar to the way ocean waves move. Love waves cause a side-to-side motion. These four waves together, depending upon their distance from the epicenter and their magnitude, can cause vast amounts of damage and loss of life. It's important that we understand how we describe various earthquakes. We rate them on a set of mathematical scales. One of them, the most traditional, is the Richter scale, which is a logarithmic scale measure of the amplitude of the waves released from an earthquake event. As a logarithmic scale, the difference between each numeric value on the scale is a factor of 10. For example, the difference in magnitude between an earthquake measuring 2 and an earthquake measuring 5 is 1,000. A 5 is 1,000 times worse than a 2. As we see that there are 3 steps from a 2 to a 5, and we multiply 10 times 10 times 10 to achieve the 1,000. The other scale is the moment magnitude scale, which measures the amount of energy released by an earthquake event. This scale is linear and is multiplied by a factor of 32, as each stage increases from one to the next. So an earthquake measuring a 5 produces 96 times more energy than a 2. Remember the differences in these scales. Lastly, let's take a look at one of the major impacts of earthquakes, a tsunami. Tsunamis occur when an underwater earthquake rapidly displaces the water above it. This rapid displacement transfers energy from the earthquake into the water, which forms a large wave. As the wave moves closer to the shore, the amplitude, or the height of the wave, increases as the depth becomes shallower. When the wave finally reaches the shore and breaks, it can be hundreds of feet high and cause massive amounts of damage. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between these topics. Then, use the statements at the beginning to review.